So this is the second lesson of limits, and this is going to be how to calculate limits. So one thing you should notice is that limits are really just the values of a function that don't exist, but they're still values of a function. So as you can see here, if the limit approaches the same value of f of x and g of x, we can just treat them as those values. So we'll add them, subtract. It's not like logs where when you multiply you add. It's nothing like that, it's just regular. Also, we're able to take constants out. Okay, so, and here's how a composite function would work. It's basically f of the limit. So, we would not use this limit c value in f, if that kind of makes sense. I'll explain it more in the value. Okay, so, first, limit as x approaches 0, so it would be f of 1 times g of 0, but remember it's approaching these values, so it's not actually them. So f of 1 is -2, and g of 0 looks to be about -1/3, something like that. And then as it's approaching that value, so f of 0 once again is 0, and then we can see here that since limit of g is approaching two different values, it doesn't exist. However, one thing that's interesting about these type of limits is that we can also evaluate from both sides. So since it's because remember the definition of a limit is limit as x approaches 2 from the right equals as x approaches 2 from the left, technically, right? So if we look from the left side, it's approaching 1. So this function would be 0 times 1. And then if we look from the right side, it's approaching -1. So 0 times -1. 0 equals 0. So this limit actually does exist, and it exists at the value of 0. Okay. And now we have an interesting composite function here. So remember what we said. Limit as x approaches 1 of g of x. So the x approaches 1 and g of x, it's going to about 1/3. So we would say this is 1/3. And then what is the value at 1/3? It is about -2/3 here. And we can do the same thing here. So as x approaches -1, we can see it approaches the value 2. And then g of 2 actually does have a value. Remember, we're not approaching it anymore. It's just g of 2, which is 1. Okay, so here's something that's called the squeeze theorem, which is kind of interesting when you think about it, right? So basically what it says is that if we have a function f of x and then two functions around it that kind of equal the same value, then f has to be that value. So let's say I had 1 less than equal to x less than equal to 1. The only value x could possibly be is 1. And I'll show you how this kind of works. So, right, we have limit as x approaches 0 of sine x over x. So what I'm going to do is I'm going to set cosine x. You don't have to know what these other functions mean. It's just part of the proof is less than 1. And then it's at x equals 0, right? So the limit as x approaches 0 of cosine x is equal to 1. And then this is 1. So 1 is less than or equal to sine x over s is less than or equal to 1. So that means that this value must equal 1. And if we kind of look at the graph, we can see that as well. So we have y equals 1, then we have sine x, and then we also have cosine x, right? You can see they all kind of meet up in the middle, which means they have the same value. And then here are some special limits you'll have to memorize. We'll talk about this more in the future with L'Hopital's rule, but just memorize these limits. And this is technically an indeterminate form. We'd usually solve this with L'Hopital's rule, but another way we can do this is multiplying by the conjugate. So then we get and then we know using Pythagorean identities. And then what we can do is we can kind of take out sine x over x, right? And then we'd be left with, and then we can actually plug these values in. So we know this one is equal to 1, and then sine of 0 is just 0, and cosine is just 0, so 0 over 2 equals 0. So it's 1 times 0, which equals 0, which would be our final answer. So I previously mentioned the conjugate method to find the limit, but there are many different methods. You can use direct substitution for ones that exist or functions that are continuous. You can rewrite the limit to maybe make it easier to read. You can take out the constants, add some constants in, right? Or you can use the squeeze theorem. So I'm going to go through some examples really quick. So secant x squared, we know that's a continuous function, so we can just plug in pi fourth, right? So we would get secant is 1 over cosine x. At pi fourth, cosine x is root 2 over 2, so secant would be 2 over root 2, and then 2 over root 2 squared is 4 over 2, or 2. Number 2, we can rewrite this as 3 over e to the x. So e to the x will be approaching infinity. Any constant over infinity we can say equals 0. For an absolute value function, what you have to do is you have to kind of treat it like a piecewise. X is less than or equal to 4, since when it's less than, that value would be positive. And then when x is greater than 4, this would make it positive. It doesn't really matter which one is less than or equal to, or it doesn't really matter which one has the equal sign on it though. So then, if we're approaching it from the left side, we'd go with the less than or equal to 1, which is just 4 minus x over x minus 4. And then if we plug 4 into that, we would get negative 1 if we take a negative out here, and get like negative times x minus 4. So in this question here, you can see that this is indeterminate form, right? It would just be infinity over infinity. So what's interesting about limits is we can kind of treat it as horizontal asymptotes. So when the degrees in the numerators are the same and it's approaching infinity, this value would actually equal 2, right? Let's say I had something like this over 3x squared. When the denominator is the same, it equals 0. And then, or if the denominator is greater. And then if the denominator is less, I would have to treat it like a slant asymptote and use synthetic division. But that is for another question. And then over here, if you remember, this looks like what we had earlier, or one of our memorized limits, but not exactly. However, what we could do is we could rewrite it as our memorized limit, which was this, and we could just square it, because remember, they kind of keep that continuity, and we said that was equal to e. Yeah. So over here, what we have going on is x approaches negative infinity, 20 over 4 plus e to the negative x. So when we plug negative infinity to there, we actually get 20 over 4 plus e to the infinity, which means 20 over infinity, and any constant over infinity we can say is equal to 0. And then for this question, we have the limit as x approaches infinity of ln of x squared over ln of x. So we'd have to kind of use property of logs here. Remember that if we square a value in properties of logs, we can bring it out to multiply. So that would just be 2 because these cancel. And then over here, remember when I said how if we had a conjugate plus a constant, we have to multiply by its conjugate. So then we get these all cancel as x approaches 0 of 1 over root x plus 1 plus 1. If we plug x here, we get 1 over 1 root 1 plus 1, which is just 1/2. And then remember when I said if we had a question, or we could start by simplifying this one first by using synthetic division, right? So we'd have -2, any value that makes this 0, and then we'd have 1x cubed, 0x squared, 0x, 8. And then we'd bring this down, multiply it by -2, add that, multiply it by -2, add that, multiply it by -2. Then we'd get 0, and then we'd move the power of this one down by 1. So this would be x squared minus 2x plus 4, right? And we can just plug those values in, and we should get a value that equals around 10. So this one here is kind of difficult to notice, but we see that we're approaching infinity or negative infinity, okay? And we know that root of x squared is going to be x. We don't care about this value for now, right? Over 2x. And this looks like the question we had earlier, where they have the same degree. So we can just do x over 2, which equals 1/2. We don't really care about the constant in this radical, because no matter what that constant is, this root of x squared will always be x. And then this one is also kind of difficult to notice, but you have to realize that it looks like one of our memorized limits, or special limits, which sine of x equals 1, but not exactly once again. So what we'd have to do is we'd have to make it look like that limit. So we have our question, and then to make it look like that limit, we can do this. And then we can take out the 7 since it is a constant. And since these two values are the same, we can set it equal to 1. Right, and then it's just our constant times all of this, which is equal to 1.